All right, we'll go ahead and start. So when we left off, we had just taken a look at this case of how oftentimes when you try to modify an object in R, change one element of a vector, for example, there are lots of occasions when that whole object will end up being copied and the copy is modified because of R's immutability property. But that doesn't not always happen, and for figuring out the cases where that doesn't happen and how to avoid that issue can lead to ways that we can make our code a little bit more efficient, make things go faster. So here in this example, we had just taken a look. We assign this vector 1 through 10 to x. We can use this trace mem function to tell us whenever an object is copied. And here we can see, so when we first start tracing the memory, we see it prints out the location in memory where it's currently stored. Right now, x is the only variable that points to this particular object in memory. If we assign a new value into the fifth element of this vector, we don't get any message from trace memory, which just tells us that that object was actually modified in place. It wasn't copied anywhere. So just that single element was actually changed. So that's very efficient. Conversely, if we assign x, that same object add x to a new variable y, now both x and y are pointing to the same object in memory. So now if we go and try to change an element of x on its own, because y is now pointing to that same object, R decides that these objects have to be immutable, so it has to create a copy. It modifies the copy of x, so now x is changed and y stays the same. So if we can take advantage of the case where x actually is modified in place, that means that gives us a chance to speed up our code a bit. And that's what we're doing here in this third iteration of our function for counting the number of missing values in the columns of a matrix. So here we're going to initialize this call NA's variable as a numeric vector with length the same number of the number of columns in the matrix. And then we're just going to update the elements of this vector at each iteration of the loop. And because there's no other variables pointing to that same object, it'll actually just get modified in place each time, so it'll be efficient in both speed and memory. And indeed, when we micro-benchmark it compared to our previous versions, we do see a slight improvement. So let's see. So now we go try to use our profile on this. Doesn't seem like there's much more we can improve. I'm not actually sure what this .make numeric version thing is doing. I'm not entirely sure what that is. I haven't actually seen that before. That's the first time I've seen that come up on these slides. Apparently it has something to do with the package versioning. That's weird. Yeah, so I've never seen that come up before. That seems to have something to do with specific versions of a package or something. So I think we can ignore that. That seems to be an anomaly. So now it seems that is.na is, again, what seems to be taking up the most amount of time besides this anomalous function and the function itself. But we've made some significant improvements, so it's going to be difficult to improve any further. Now, one thing, if you programmed a lot in R before, if you've tried using for loops in R before, you've probably run into the case where someone tells you to use the apply family of functions instead. So you may be familiar with this a slightly more idiomatic way to accomplish this sort of thing in R. Because here we're just using a for loop to loop through the columns of X and doing a calculation at each iteration and assigning to the elements of this out vector, essentially. And so another way to do that that's a little bit more idiomatic R code is to use the apply function. So just like L applies a function to each element of a list or vector, apply applies a function to each row or column of a matrix. It's actually a little more general than that, and it can apply a function to the margins of any array. So you can actually apply things over 3, 4, 5-dimensional arrays and so forth, sliced through in different ways. But most cases, you're just applying things to rows or columns of a matrix. So the first argument here is the matrix itself, the dimension that you want to apply things over. So here, 1 corresponds to rows, 2 corresponds to columns, and the way to keep that in mind, especially if you ever end up using apply on higher dimensional arrays, is those just go in the order of the fastest moving dimension, essentially. And in R, matrices are stored in column major order. So if I have a matrix N, M, this is just a 10 by 10 matrix. How this matrix is actually laid out in memory is sequentially the columns are contiguous to each other. So this first column is contiguous in memory, followed by the next column, followed by the next column, followed by the next column. And the way that we can check that for sure is if we convert it to a vector. We can see that that's exactly the order of the elements themselves. In fact, another way to create this matrix would be to just create a vector from 1 through 100. If we assign dimensions to that vector, it will become a matrix. And so that going through the rows here, this is the fastest moving dimension, followed by the columns, and then if this were a 3-dimensional array and you imagine a third dimension coming out here, that would be the third dimension then. So here, the first one is the rows 2 we're applying over the columns. So for each column, we would just want to apply this function, sum up the number of missing values, and then that will be returned, and apply will automatically simplify that and return it to us as a numeric vector. Now, let's go ahead and micro-benchmark that. You can see the results right here. So if we compare our 4 different versions of this function, you've been told before, don't use for loops in R. They're very slow. Use these apply functions instead. In this case, what we find is this third version that uses this apply function is actually quite a bit slower than the last 2 versions of our function that just used for loops. So this is a lesson that it's not always true that you should avoid for loops in R. There are occasions where a for loop is just going to be better. In particular, the apply function here is not as optimized as lapply or sapply. The apply function here for iterating over a matrix, it actually just uses a for loop essentially internally as well. The lapply function is a little bit more optimized, so there are times when you can eke out a little bit of speed improvement just by using lapply in place of a for loop. But for iterating over rows or columns of a matrix, apply is primarily used because it's more expressive and can sometimes be easier to write than a for loop, not because it's actually faster. So here, if we take a look at how much time is being spent in this version of the function, we see a lot of the time is spent In apply, that's obvious. That's how we wrote the main thing that we had in the function. And then the next most amount of time is taken up in this aperm.default function. And that's because, well, first let's see what, well, let's take a look at the name of this function. Who can tell me a little bit of information about what this is just based on the name here? Aperm.default. What is this? It's the default method for some generic function called aperm. I heard a few people saying something similar, like something like that. So, good. All right. So aperm.default is the default method for a generic function called aperm. What that does is it transposes an array. So it's like just transposing a matrix, but it's a more generalized version for arrays as well that can work for higher dimensions. And the reason that seems to be taking up a lot of time is, as I mentioned, this apply function is very general and will work for higher dimensional arrays as well. So in order to program it in a very general way, the apply function ends up permuting the dimensions of the array to make things easier to calculate. And so a lot of time is actually spent just shuffling the data around in this permutation. Yeah?
Can you briefly explain the difference between a matrix and an array?
Right. Okay, so in R, there is no difference between a matrix and a two-dimensional array. If we want to create an array specifically, there's a function called array that will create arrays for us. So let's say I want to create a three-dimensional array. Oops. So here, this is just a three-dimensional array, so I can index into it in 3 places. Index into it works just like you would with a matrix, except you have one additional index. So one thing to note about matrices and arrays in R, they're just the same type of either integer or numeric. The class is array, but unlike most, they do behave slightly differently from other S3 classes. So I'm not 100% sure whether to consider them S3 classes. They do behave slightly differently. So for example, I showed before how the only actual difference between a matrix, an array, and a numeric or integer vector in R is the dimension attribute, the dim attribute. So here, excuse me, another way to do that here, A is just right now an integer vector from 1 through 27. It has no dim attribute. So if I just set the dim attribute to 3, 3, 3, A is now an array. Likewise, if A were, I can also make A into a matrix just by modifying the dimensions. And let's say, let's use the array function to create a 2D array. And that is a matrix. So here a 2D array is the same as a matrix. And the only real difference between a matrix, an array, and a regular numeric or integer vector is just that dim attribute. So internally in R, the data itself is stored exactly the same way. And the only difference is that dim attribute. So there's no actual real difference between a matrix or an array, or even just an integer or numeric vector in R.
Can you give it an array, like row and column names, even if it's 3 names?
You can give it dim names, yes.
Oh, cool.
So let's see. So let's make that 3-dimensional again. Right. So it's rows, and then columns, and then whatever the third dimensions are. And so remember, you can always kind of figure that out just by how the matrix gets formed if you start off with a simple vector. So here I have a vector. So somewhere this is stored in memory as just a sequence of 100 integers. And that's still going to be true once I turn it into a matrix. So if I add dimensions to this, then these are going to go by the rows first, then across the columns, and then a third dimension, and so forth. So if I wanted to add dim names to this, well, because this is a matrix, so I can just use the shortcut row names and call names. But let's do it with an array. Let's see, dim. So now we have a 3 by 3 by 3 array. Let's give those dim names. That has to be a list. Letters is just a variable that is included. It's just the letters of the alphabet. And now if I print that out, that array will have dim names associated with each of those dimensions. So yeah, so dim names, these are a few special attributes that get treated a little bit differently than any other attributes in R, because things like dim and dim names are essentially the difference between regular vectors and matrices and arrays. Otherwise, there's no real difference in how those things are stored. Any more questions on that? Some useful things to know. Okay, so here, this aprim.default, this is taking a lot of time because apply is a very generic, is a very generalized function. So it can deal with multi-dimensional arrays, and it deals with some of that complexity by permuting the dimensions, so it's easier to calculate on. And so a lot of this time is spent not just in the for loop, but also just shuffling around the data to make it easier to calculate in apply. Finally, another thing that we can do with this function that's much, much simpler than before. So before, we were using a loop to accumulate the sums over each column of this matrix. Just like we realized originally that we could just use, in those original motivating example where we went from using a loop to get a summation over a vector, and realized we can just use the sum function. Likewise, there's actually just a call sums function that will do what we were doing in a loop before. So this will just sum up the columns of a matrix. And the other key thing in figuring out how that this works is that is.na itself is both vectorized, and it will return an object with the same dimensions as what you gave to it. So here, well, I already have an array here. So let's just do is.na on this array, and it actually just returns an array of the same dimensions. It even has the same dim names, but now it's just a logical array with whether individual elements are missing or not. So that means if I apply is.na on this matrix, it returns a logical matrix, and I can just sum up the columns of that logical matrix to get the number of missing values. And now there's not much to be gained anywhere in terms of trying to optimize that. And we can see if we time that, that is quite a bit faster than any of our previous attempts as well. So those are another useful thing to know, is that things like functions like call sums and row sums exist. There's also a package called matrix stats that implement these sorts of calculations for many other sorts of statistics. So calculating medians, variances, standard deviations, and things like that efficiently over all of the columns or rows of a matrix. So there's a package matrix stats that's dedicated to that as well. But call sums, row sums, call means, and row means, these are in every R installation and very useful. All right, so that's about as good as we can get on staying in R itself. And that final version is pretty much just using pre-vectorized R functions that basically go straight into C code and are very efficient. Now let's say we wanted to actually, it's good for us that those functions exist and they're written in efficient C code, but suppose we wanted to write some sort of C code ourselves for functions that did not already exist for us like that. So there's a really good package called OurCPP that makes it really quite easy to write C++ code and integrate it with R. It is perfectly possible to write C++ or C code and incorporate it with R without using this OurCPP package, but it is quite a bit more difficult, and you have to know a bit more about R internals workings if you do it the hard way. So there is this .call framework that allows you to run compiled C and C++ code without using the OurCPP package, but writing code using these frameworks can sometimes be quite a bit ugly because you have to start worrying about not just your own C, C++ memory management, but also R's garbage collector and things like that. So this package, OurCPP, makes it very easy and provides a lot of syntactic sugar that makes it almost like you're working with native R data structures. So as a simple example, suppose we have this simple function add1 in R that just looks like this. We use the function to create it. We just give it x as a parameter, and we return x plus 1. How that looks in C++, well, first things first, we have to decide what kind of variable x is. In R, we don't have to declare what types our variables are. In C++, we're going to say that x is a double. So that means the same thing is not going to work on integers and things like that. So here we have a function called add1c. It takes a single parameter called x, which is a double, and it returns a double. And in C++, to return something, we write a return statement. We return x plus 1 as semicolon to end the line. And in OurCPP, this is not typically the way you would end up writing C++ code, but it provides a nice way to get started. There's just a function called CPP function, which will compile whatever C++ function you give to it and lets us call it from R. So running this CPP function from the OurCPP package will compile this function, and it will create a new variable in our global environment called add1c, which is a function that uses this .call framework that I just mentioned. It does all the dirty work for us, so we don't have to worry about R's garbage collector or things like that. And it ends up that we just have a function that we can call from R that evaluates this C code. Yeah? Yes, so it is compiling this C++ code, so you do need a C++ compiler. I have actually not updated to the latest version of R. It seems like they're using a newer C++, a newer version of Clang that isn't included by default on Macs now, so that's something I still need to do. Older versions on Macs, it was really easy. You just installed from Xcode. Windows, there's a separate RTools executable that will install all the Windows tools you need. Linux, you should have everything already. There's a new page on that Kren will link to for downloading the new compilers for Mac as well. All right, so if we test those, we have these two functions. Add1, we wrote this in R. Add1C, we wrote this in C++. And they work the same. I guess it turns out that OurCPP we will be able to pass ints to that. I guess those just do get typecast correctly, but lots of other times that won't end up working. All right, so the way we would implement our call NA's function in C++. So this would be in a separate file, a separate .cpp file. And it actually ends up looking a lot like our original code when we first wrote this function, the first version of our function in R. So we start off with include statement. We got to include the OurCPP header. We're going to use the namespace OurCPP so we don't have to qualify that we're using OurCPP for all of the OurCPP functions and classes here. And so now, kind of like Roxygen, OurCPP uses code comments to handle some of its exporting and importing shenanigans. So here, having this code comment OurCPP export tells OurCPP when you compile it with OurCPP that you want this function to be exported to the user and be able to use this. So what we have here, we have a function. We have it called call NA's C1. It takes a numeric matrix X and returns an integer vector. We declare the integers, number of rows and number of columns. So these numeric matrix, integer vector, these are classes that are implemented by OurCPP that wrap the sort of ugly R objects. So R's interpreter is written in C, and the C objects for working with like R matrices and vectors are not as nice as this on their own. So they're kind of ugly C structs from the 70s. So OurCPP is really nice because you can work with these like modern C++ classes. Use methods to get the number of rows, number of columns. We're initializing an out integer vector that we're going to be returning. And now we're looping through the number of columns, getting the number, initializing the number of NAs, looping through all of the rows in a column, checking whether each element is missing or not, incrementing that number of NAs, and assigning that to our out vector, and then finally returning that. So very, very close, actually, to the first version of this function that we wrote. So to compile and import that into R, OurCPP has this source CPP function. So that will compile and load that function into R. I believe I included that. Yeah, I have a folder that includes 2 versions of this C++ source code on Piazza. I'm going to set this to my working directory so I can run This is the version that we just looked at. I can run OurCPP. We can see it's compiling it with Clang, and now I should have a function called colonnades C1 that will call that C code. First things first, we want to make sure it actually is doing the same thing as our own original function. We get the same results. And then we can do some benchmarks and see how it performs. So our version in C takes about almost the exact same amount of time as R's own version, which itself mostly uses C code, because we just have 2 actual R function calls, and then those go pretty much straight into C code. And one thing cool about OurCPP, I mentioned it has a lot of really nice syntactic sugar. So we can actually simplify that original version as well in kind of the same way we simplified the R version. Not quite as much, but we can simplify that inner loop. So OurCPP's isInA function is also vectorized. It will also work on a vector. I don't think it will work on a full matrix, so we can't simplify it quite as much, but we can get the column, apply isInA in C++ to the whole column. OurCPP provides a sum function that has the same functionality as R's function, so it'll sum up all of the trues in this logical vector, and then we can return that. So here, this simplification is basically the same thing that we did the first time we simplified it in R as well. So that's some really nice syntactic sugar that OurCPP provides, is being able to use some of those same vectorized operations at the C++ level as well. And so if we compile that using OurCPP and then benchmark that, we get about the same speed as the last 2 times. These are close enough to be probably indistinct from each other. So ultimately, in this case, we can do essentially just as fast whether we write the C code ourselves or just call R functions that pretty much immediately call C code. I'm not going to go too much in depth on this, but if you want to use OurCPP in a package, in the description file, you would just add these 2 lines linking to OurCPP, and then of course, since it's a package, you would want to include it in imports, or it depends, but imports is probably where it belongs. And then in the namespace, you would add this directive useDynLib. So that's telling the namespace that you want to use the dynamic linked library for your package, and you want to import the OurCPP package. If you do want to use OurCPP in a package and you're starting a new package, OurCPP also provides its own version of package.skeleton. So you can just use OurCPP.package.skeleton in place of R's built-in version of package skeleton to set up a full template for you, including all of the OurCPP stuff. And then if you're using DevTools, you can also just use their use OurCPP function, and that'll set up the templates for you to get started with the OurCPP code as well. So of course, when you, because OurCPP is an additional layer, so when you build the package, R has to know about the OurCPP code, so you kind of have to compile it in 2 steps, which is not the case if you were not using OurCPP and you're using R's built-in mechanisms. But OurCPP makes coding in C++ so nice that it's usually worth this effort. So OurCPP compile attributes is a function that will compile the OurCPP code for you. And if you're using DevTools, DevTools will automatically do that for you as well. All right, so any questions about the OurCPP stuff or this other benchmarking optimization issues? Okay. All right, so One other thing I want to point out is just some useful debugging tools to help you. Turns out lots of people don't necessarily know these exist. But one major problem with programming is you almost never do something correctly the first time. It would be really nice if you did, but that's usually not ends up working out. Once in my life, I coded a complex thing and it worked correctly the first time. And that has never happened again. So debugging is really important. And so here's a few useful functions if you have some R code that you're running into errors and you have no idea how to fix them. So first, the most simple step is the traceback function. So if you run into an error in R, the easiest thing to do at that point to start diagnosing the issue is to just type traceback, do that function, and that'll just print the stack at the time that the error occurred. So that means it'll print all of the functions that were being evaluated at the point that the error happened. And that's useful because you can find out where the error actually occurred and whether it was in this function or that function. So the last point in that traceback is where the error occurred, and it can be helpful to figure that out. The browser function is basically R's version of a breakpoint that enters a debugger. So browser is a function. When it's executed, you will enter a debugger, basically. And you can kind of use it as a pseudo breakpoint by just inserting it manually into your code, where you would put a breakpoint in a normal IDE. RStudio actually does support breakpoints as well. I don't use them much myself, but I'm told that it does. Another option is there's this options error equals recover. And this can be useful, again, if you're trying to hunt down an error and you're not sure where it occurred or why. What this does is when an error occurs, R will take a moment and decide what to do based on what this option is. Recover means that it will enter into the browser, it will enter into the debugger at the point where that error occurred. And you can set this to null if you don't want that to happen. So after you do this, you typically want to set this error equals null so you don't have it entering the debugger at every single error. And then lastly, there's this debug and undebug function, and that just tells R to enter the browser, enter the debugger automatically whenever it encounters that particular function call. So you apply debug on a specific function, and then undebug it when you're finished debugging that function. So I didn't have any prepared examples of this, but let's make one. So we'll just make a simple function. So here, it's just a simple example of how this, well, first, let's just do this. All right, so here's just a simple function, takes arguments x, y, z, and then it prints each of those arguments. So let's say foo1, 2. So there is an error. Argument z is missing with no default. You can check the traceback. In this case, it's really simple because we just called the function where the error was directly from the command line, so this traceback is very small. Let's make that slightly more complicated by adding a few more functions. So you can see those a little bit more easily. There. So that all fits on the same screen. Okay, so let's do baz1, 2. All right, so we got an error, print z, argument z missing with no default. The function that we had done when we got that error was baz. If we do trace back, we can see, okay, at the top of the stack was baz. That's the function we executed. That function called bar, that function called foo, and foo called print, which is where the error occurred. And so in this case, it's pretty simple. We already have the functions. We know what they're doing, so it's easy to see where the error occurred. But if you're using like calling some sort of modeling function from a package, there could be some error way down the line where that function calls a function from another package, that function calls a function from another package, and the error is all the way over here when you are using the function that was over here, and you need to figure that out. So this traceback is just a very useful, simple first step of figuring out where that issue actually is coming from. Because you can see what functions were being executed when the error occurred and what was the last one that was being executed. Okay, so now let's put a call to browser in this foo function. I'll call baz12 again. And in RStudio, this is set up nicely, so this will actually take you to an approximation of the source code itself. What you would typically see if you're just at a terminal is just this part. RStudio also has these nice buttons to tell you give you different options for what to do. So execute the next line of code, jump into a line of code, continue, or exit the debugger. So those are very useful if you're in RStudio. So here you can use those to step through each line of a function. If you're don't happen to be in RStudio, there are commands that you would use to do each of those things instead. So when you're in that browser, it's just like a debugger if you've ever used a debugger in another language in a command line. So if you type n, that just executes the next line of code. S executes the next line and steps into it if it's a function. F, finish execution of the current loop or function. C means continue executing and keep executing until you're done. Don't show me the rest of it. Don't stop again. And capital Q just is to quit the debugger. So that's how we can step through the function with browser. If you don't have, of course, the main thing with browser is you do actually have to have access to the source code to put that into it. I think in, RStudio will also allow you to set breakpoints that behave as if you had placed a browser call there. If you do not have access to the source code to do that, say it's in a package, or well, you should have access to the source code of everything in R, but if you can't edit the source code, then there's a couple things you can do. So we discussed one option is options error equals recover. So if I do that, when an error occurs, it'll give me the trace of all of the functions on the stack at that point, and it'll ask me where I want to jump in. So I want to jump into the foo function, and so that'll put me inside this foo function. And also at the browser window, we can still use other commands, ls, so forth. Let's see. So one thing is if you happen to have a say you have a variable in here called c or a variable called n, well, you won't be able to print the values of those very easily because those correspond to commands to the debugger. So you want to use some other way to get those. So either get the name of those variables or print the name of those variables or something like that. I can also do debug on the foo function. And that will put me into the debugger whenever the foo function is called. And so that's another useful way if you want to debug a function in, say, someone else package to figure out what's going on, what the issue is. You can just use the debug function on whatever that function is. You don't have to have the source code or be able to edit it or anything like that. And then that can help you figure out what the problem is. And then when you're debugging it and you don't want to go into the debugger every time that function is called, you just call undebug on it. One other useful thing is sometimes you want to debug warnings rather than errors. Sometimes you get a bunch of warnings, you don't know what they are, and you would like to debug those, but you can't because all of these debugging tools are designed around errors. So you can convert warnings to errors by changing the options warn equals 2. So warn can be different integers. They correspond to slightly different behavior when you get a warning. So if you set warn equals 2, that will turn them into errors. The default is warn equals 0, so you can set it back to that to return to the default behavior. But if you want to convert warnings to errors to make them easier to debug or just stop if you get a warning, you can set options warn equals 2. Any questions on debugging on that so far? How's everyone doing? All right, let's see. Quickly go through this. Yeah.
For when it comes to warnings that you don't have to set,
Mm-hmm.
is there a way to suppress them?
There is a function called suppress warnings that will suppress warnings. Does that answer your question? Okay, so I'm going to do a quick look into an example where I was trying to figure out how to optimize a particular function myself a little while back. So in my research, I primarily work with mass spec imaging data. So here I'm just going to create a very simple data set that represents imaging, not specifically mass spec, but just imaging. So here I'm creating let me get out of this. And all right, so here I'm going to create a simple data set. So IMG, this is just a data frame with X and Y pixel coordinates, and then values for those pixels. Now I'm going to plot those in ggplot. And so in this very simple example, my values are just a sequence from 1 to 100, so my image just looks very boring like this. But it's really easy to plot. So I have a package called Cardinal on Bioconductor for the analysis of mass spectrometry imaging data. And when I was first writing that package, I made a basic assumption that all of our imaging data, the pixel coordinates would be on a fixed rectangular grid. And for the vast majority of data sets, that is true. Lately, we have been starting to get a few data sets either using nanodesi or now using 3D mass spec imaging, where the pixels are not necessarily on a fixed rectangular 2D grid. And so let's say we add a tiny bit of random noise to those X and Y pixel coordinates to simulate pixel coordinates that are not on a perfect rectangular grid. Now what happens if we try to plot the image using any regular plotting method like in ggplot or even using R's own image function? Well, we don't get an image at all because now the coordinates are not on a regular grid. So that makes them difficult to plot. So this is what that data looks like after adding just a little bit of noise to the x and y. But it makes it so it's difficult to plot them because most of these plotting methods, whether they're in ggplot2 or R's base image method, which is another way for plotting images, expect the data to be on some sort of regular grid. So recently I wanted to try to write some extensions to allow us to work with data that is not on a fixed grid. So I needed some way to project these non-gridded coordinates to a gridded coordinate system so most of our regular imaging methods can still apply. So I came up with this function called project to raster. It just projects x, y coordinates that may not be on a grid onto a grid. So how this works is x and y are numeric vectors. So x and y are the pixel coordinates. Z is the values for the color of each pixel. And then dim I'm going to have as a user-specified parameter that decides the dimension of the raster. So the resolution of the image, essentially. So here I'm getting the number of rows and number of columns as the values of dim, getting the range of x and y. And so here I'm basically doing a calculation to calculate the approximate resolution of x and y. So the standard step sizes between the x and y coordinates. And then I'm going to create a vector that is going to become my raster. I'm going to turn that into a matrix with the number of rows and number of columns as that dim parameter. And then I'm going to loop through all of those z values. So these are the colors of the pixels, essentially. And basically do this calculation to project if this x, y coordinate were on a fixed gridded pixel location on a grid of this size, where would they be? So that's calculating the gridded row and column number of each element of z, and then I'm going to return that as a matrix that can be plotted as just a image raster. So doing that, that seems to work. But now, one thing I'm concerned with is I want all of this to be very interactive. And if the image is very large, I want all of that to be instantaneous. So I was looking at this, and I figured there must be a simple way to avoid looping through all of the elements of z here. Because while thinking through the original problem, it was easiest to think of each element of z individually. But as it turns out, as is often the case, it's also possible to just rewrite that as a vectorized expression instead. So here, instead of calculating the projected x and y coordinate of each pixel individually, it's actually possible to just calculate them as a vector and then do a little bit of adjustment, and then add all of those vectorized into the image raster. So I won't bother going into much more detail on that. It's just a recent example of how I was looking at a problem, originally wrote it in a for loop, and then figured out I could just rewrite it in a vectorized expression that's much faster. And to test it, make sure both of those functions are returning the same thing. Created a couple of functions to apply those functions to some data, and then use microbenchmark to see how fast each of those are. The first one using the for loop takes about 253 microseconds, and the second one takes 26 microseconds, so about an order of magnitude faster. So that's nice improvement. Okay, any questions on that or on this performance debugging profiling topic? All right. So let's move on to scalability. All right, so as a motivating example, let's go back to this twin experiment that we were talking about earlier with examples in the tidyverse. So suppose we want to test all of the proteins for differential abundance. And Tsunheng showed us how to do that earlier on using the tidyverse. But it took a little bit of time to do it. So suppose we want to do that, but we want to make it faster. So first, I'll go ahead and load the tidyverse and Broom, load the data, reformat it slightly, create a function for normalization. This is just the same median normalization we've done before. And I'm going to normalize the data and filter it so I just have the light channel. So now this is my normalized data, and I just have, this is my normalized data, and I have just the intensities of interest, so just the light channel. And now, what I want to do is I want to write a function that tests the differential abundance for each protein in that data set. So I'm going to do that by writing a function, and there's going to be two main steps. The first thing I'll need to do is to summarize the intensities for each protein based on all of the features and runs. Once I have the intensities summarized for each protein, then I'll just go ahead and do a t-test on that data. So here, this is my function. I'm first making sure the tidyverse and Broom are loaded. I'm fitting a linear model that will let me summarize the intensities for each protein. I'm tidying that model, getting the fitted estimates, and renaming them to run and intensity. Then I'm going to join that back with my original data. So test data here is my summarized data, summarized for whatever protein this subset of data is looking at. And I'm going to do a t-test to test for differential abundance based on zygosity. So this is all more or less from Tsunheng's earlier slides, if you want to take a look back at those to figure out what's going on here. But should be relatively straightforward. Okay, so I just wanted to have that as a simple function, so I can just apply this function separately to each subset of the data for each protein. So now let's see how long does it take to fit this model for all proteins. So here to do that, let me first create that function. So here I'm going to take the data, group by protein, nest, and that means I now have a list column of data sets where each of these data sets is a subset of the data corresponding to each protein. So I can just apply this model fit function to each element of this data list column, and that'll just be applying that function to each subset of data corresponding to each protein. I should actually rename this fit, because I'm returning the whole thing. So let's see how long that takes. It doesn't take too long. So 5.6 seconds. Not too bad, but this is also a relatively small data set, so we can imagine if it was much larger, if we had a lot more proteins, that could take a longer time. So in this example, we're basically applying the same function to a bunch of different independent subsets of data. So that means it should be really easy to parallelize this, because each subset of data doesn't really care about any of the other subsets of data. So there's a package on Bioconductor called BioCParallel, BioCParallel. I'm never sure how to pronounce that when they have the BioC consonant afterward. BioCParallel on Bioconductor, it provides a function called BP lapply for BioCParallel lapply, which is just a parallel version of lapply. The nice thing about the BioCParallel package is that BP lapply will still work if you don't have any sort of parallelization or multiple cores or anything like that. So by default, it will typically just either run in serial or whatever is most optimized for your computer. So for cross-platform compatibility, BP lapply allows users to register different parallel backends. So you just have to write BP lapply, and then people can choose how they want to run that in parallel. So it provides several different parallel backends, including, as I mentioned, a fallback to just running things in serial like a regular lapply. So the two parallel versions that we'll be talking about is multi-core and Snow. So multi-core implements a shared memory parallel backend that uses forking on Unix-like operating systems. So this multi-core version is only available on Mac OS and Linux. That's not because the authors did not like Windows. It's because it relies on an operating system utility that is only available on Unix-like operating systems. So how this multi-core version works is it basically creates clones of your original R session, complete with the exact same data sets, the exact same packages that are loaded. And that means it's very, very easy and typically relatively efficient, because you don't have to worry about sending your data sets over to those new sessions. You don't have to worry about making sure your packages are loaded on them either. And typically it can be somewhat memory inefficient in that they will try to use the same, share the same memory as the original R session. That does not always work, but they try. So that's multi-core. Snow uses this simple network of workstations parallel backend. And what that does is it starts brand new R sessions that are networked via socket connections. So multi-core makes clones of your original R session. Snow starts brand new, fresh R sessions that you then talk to from your original R session. So with Snow, you end up having to make sure your packages are loaded on these new R sessions as well. So it requires a little bit more babysitting. So what BP lapply looks basically just like lapply. You have X, which is just some sort of list-like object. X does not actually have to be a list. It can just be any object with a length method, and that can be indexed via the bracket and single bracket and double bracket. Fun is some sort of function to be applied to each element of X in parallel, and then the ... are any additional arguments that you're going to pass to fun. And then BP param, this is the parameter that decides what parallel backend to use. So whether this is going to be executed in serial, or using multi-core, or using Snow. And the default for this is this BP param function, which will just find the default registered backend. And what that means is, so I'll load up BIOC parallel. So there's a registered function. This will tell me all of the available backends on my computer. I'm on a Mac, so the default is multi-core. Snow is also available, and then serial is also available as a fallback. So these are all my possible registered backends, and then BP param will just choose the default one. So in my case, that's multi-core. And users can change what registered backends they have, what the default one that is used. So typically, you will just leave this BP param as it is and allow users to set whatever additional options, register their own backend, and then BP param will find the one that the user wants to use automatically. All right, so how that looks now. So first, we'll just make sure that it actually works in serial. So let's go ahead and do that. So that takes about as long as the as it originally took just using lapply, because it's basically the same as lapply. You can see twin fit. This now has, this should be fit, not key value, since I have the full output object here. So now I just have a bunch of hypothesis tests for each of those proteins. To set it to multi-core, so I can create a backend using the multi-core param function. That can take several arguments. I'm just going to use the workers equals 4 argument to say I want 4 workers because I have 4 cores for hyper-threading. I have 2 real cores. Supposedly, I effectively have 4 cores. So now MC, this is just the multi-core backend. So this will work by forking my original R session. Oops. I missed the last couple parentheses there. And so that was about half the time as before. So in this case, the data set is relatively small, so we don't have a whole lot to gain. It looked like it took a lot longer because I forgot to type the last 2 parentheses, so it didn't actually start running until a couple seconds ago. But so that's pretty good. So that will run that in parallel via the multi-core by cloning my original R session. So a few notes on that. That's Mac OS and Linux only. The original R session is forked, so you have access to all the objects and packages from your original R session, so you don't have to keep track of very much. The worker R sessions share the original's memory, so in theory, it shouldn't use any additional memory. In practice, R's garbage collector can still trigger divergent memory issues. You can still have large objects being copied on each individual worker. So in practice, this is still going to end up using additional memory, even though in theory it shouldn't, but it usually will.
So how does the vector get split into the different cores?
Let's see. Well, so with lapply, we're assuming that each element of this vector this function can be applied independently to each element of this vector. And so in this case, we're using multi-core, so we're forking the original session, so all of our data will already be available there. So this whole data set will be available, as well as the earlier data sets that I made here. So there's very little that's actually sent back and forth in this case with multi-core. With Snow, basically whatever we give to BPL-apply will be sent over to each session. And you do have to be careful a little bit with that, and we'll talk about some ways to be careful about sending too much data over or dealing with large data sets and sending those to your other R sessions. So with Snow, I'm going to set this up. I can make a Snow backend with the Snow param function. I'm going to keep it with 4 workers. And I'll go ahead and fit that. And so in this case, there's enough delay from sending the data back and forth and loading packages that we ended up at about the same amount of time as just running it in serial. Of course, if this were a larger data set, that would probably make up for that, and we would end up saving time. In this case, it didn't help much. But we can see that we get some messages from packages being loaded, and that's also why up here I have required tidyverse and required room, because otherwise when the worker R sessions try to execute this code, it'll get to tidy. It'll be like, what the heck is tidy? Because the tidyverse and room have not been loaded on those R sessions. So here I have them required as part of the function so that they will be loaded on those R sessions as well. And that also means that if we want to use any additional variables or R objects besides the ones that we're passing to BPL-apply, we have to pass those as additional parameters to that function as well. Otherwise, those worker R sessions won't be able to see them. So the cluster starts fresh new R sessions, requiring packages to be loaded. R objects to be used on the workers must be passed as parameters to BPL-apply. And if you have more of those objects besides the actual data set and function, you can pass those via the ... and make them an argument of whatever function you're using. Mm-hmm. Mm-hmm. Mm-hmm.
In the cluster, each computer node might have a number of cores, so
Mm-hmm.
will there be a problem if the number of workers is defined more than the available cores?
There won't be a problem. So, I mean, everything will work fine. As far as the optimal number of workers to choose when you have a cluster, that is a problem on its own. So that's something that you kind of have to figure out according to your own cluster and the size of the data. But there won't be any actual problems in terms of things being executed and everything evaluating properly.
So in your computer, if I define workers equal to 100, it just works just as workers.
It will work. I imagine it will work very slowly because we're creating far more processes than we need. So that would create a huge amount of unnecessary overhead. Everything should end up working, but it would be very inefficient. I can go ahead and at least try setting this to, say, 10 and seeing what happens. So this may take a couple seconds longer, but it should be fine. Yeah, so the extra overhead from those additional workers means it will ended up taking about twice as long, but everything's going to execute fine and it'll be fine. But yeah, so how many workers you want to create is, you'll want to do some figuring out in terms of your own computer, your own cluster, and the size of the data set to figure that out. All right, let's see. So a few more notes on BioC Parallel so far. In this case, the data set is relatively small, so we don't really see much improvement. But that's because in our case, the overhead of just loading the packages, moving the data back and forth between the R sessions, the overhead's greater than the gains in this case. But in other cases where the data set's very large and there's a lot to be gained from parallelization, that won't necessarily be the case. When using BioC Parallel in packages, we mentioned you should not specify that BP parameter yourself. You should leave that as the default so that the user can set their own preferred backend. Okay, so that was, in this case, we had a fairly small data set, and it was easy to split up the model fitting between different subsets of the data set and push that onto different workers. But suppose we have a larger data set and want to just fit one linear regression to this large data set. So here, I put large in quotation marks because this is not, I still want to run this in a reasonable amount of time for you. So this is actually only 80 megabytes. But it's just large enough to show the effect of running it in different ways. So here we're just going to fit a linear model for this data set. Oh, so this data set I'm just simulating a random data set that's appropriate for linear regression. So I'm creating a vector of coefficients, basically doing the reverse of a regression and then adding some noise. And now I'm just doing a regression of the response y on all of my explanatory variables. And so I get these fitted coefficients for this single linear model. Now the question is there any way for us to do this in parallel? So there is this idea of divide and recombine. We essentially used this idea of divide and recombine before with by dividing our data set into subsets, fitting an independent model for each protein, and collecting the results. But now we're going to use this divide and recombine strategy to essentially reconstruct a single, the coefficients for a single model based on multiple models fit on different subsets of the data. So here we just have a linear regression, y equals x beta, and suppose we divide the data into some number of subsets so that each subset is relatively equally sized. Then for each subset, we're going to calculate the coefficients, and then the divide and recombine estimate for the coefficients, if we had fit the linear regression on the full model, is basically just the average of the fitted coefficients on each of the models for the subsets. And this seems so simple that it can't possibly be true, but as long as you can assume certain things about the data set, it does work out. So here's a paper from Bill Cleveland's group at Purdue on using this technique with Hadoop and an R implementation of Hadoop. So fairly basic idea. So we want to partition the data set into subsets, fit models for each individual subset, and then combine the results. So here, there's this package called model R. It's part of the tidyverse. It has this function called resample partition that will partition the data according to proportions that we give to it. So we're just going to say partition the data set into n different pieces, each of size 1/n. So I'm going to use n equals 10. So each partition will be 1/10 of the total data set. And we're also going to make a function for obtaining those divide and recombine coefficients. that we're just going to get the sums of the coefficients and divide by the number of models or the number of subsets that we fitted. So basically, we're just getting the average of the coefficients that we found from the fitted models. All right, so how do we do that? So here I'm just creating a simple function like before that will fit the model, giving a subset of data, and I'm doing BP apply on this data set. First, I'm just going to run it in serial to make sure everything is working. So these are the original coefficients from fitting the model on the full data set, and these are our divide and recombine coefficients from fitting 10 separate models and averaging them together. And overall, they're pretty close to the originals. All right, so here with serial evaluation, the DNR coefficients are a pretty good estimate for the full model. The problem now is we have a larger data set than before, so exporting the data to each worker will require more overhead than it did before. So we would really like a way to share the same data structure between different R sessions. And while the multi-core paradigm will do that in theory, in practice, that doesn't always end up working. So we would really like a data structure that keeps only a small amount of metadata in memory and can be passed easily between R sessions. So one way to do this is we're just going to get the indices of the of each of these subsets rather than the actual subsets themselves. So here we're just getting the row indices of our original subsets that we created. So now we just have a list length 10 that has all of the row indices of the subsets of the partitions that we used. And now we can use these to figure out, to find what subset to use on each worker. Okay, so now we need the data structure itself. So I have a package called Matter on Bioconductor. It provides various on-disk data structures that mimic native R data structures. The important thing is the data is stored on disk. Only the metadata is loaded into memory, so the actual data that's in memory is very, very small. Most of the data is just stored on disk, so it's really easy to pass the in-memory part between R sessions. So I'm going to load this Matter package. I'm going to coerce the data into a Matter data frame. That's what that looks like. So here we can see 1 million rows, 10 column on disk data frame. So the object itself is about 62 kilobytes in memory and 80 megabytes on disk. So here, using this as.matter function, converts the data to a matter object, and it does that by writing the data to a temporary file on disk and returning the metadata as this R matterdf object that we can basically treat like an ordinary data frame. And then the data will be read from disk whenever we index into this special matter data frame. Okay, so now we want to apply this linear modeling function over the subset indices of our subsets rather than the actual subsets themselves. So what we're passing to the worker R sessions is just this list of the row indices of each subset and the metadata of where to find this data on disk. And so we're going to do that by, for each vector of subset indices, we're going to use that to subset the data frame. Use drop equals false to make sure it stays as a data frame. And then we're going to do lmfit on that. Here we're doing the multi-core. Now this ends up taking a bit more time than before because in our case, we added a significant amount of overhead by writing the data to disk and reading it back from disk. So that adds a huge amount of overhead. So normally you wouldn't want to do this if your data already actually fits in memory. The primary advantage of this is if memory pressure is already a limiting factor in your analysis, in which case reading things from disk in an efficient way will be faster than swapping to disk in an inefficient way. So now we can check the fitted coefficients. They're still pretty good, pretty similar to before. This is the same thing using Snow. I had to change a couple things just a little bit. So here, remember, multi-core forks my original R session, so I have access to all of the same data objects and packages. When I use Snow, I have to make sure that any required packages are loaded. I'm also passing here before. I actually use this lmfit function inside another function. With Snow, even that won't quite work because it won't be able to find that lmfit function. So I'm passing the lmfit function as a parameter, and I'm passing the data itself as another parameter. So I have to do this so that the workers are able to find this function, this data, and make sure the package is loaded. So this is just a few additional steps that you have to do to make sure your packages are loaded and all of the objects that you need are available to the workers when you're using Snow. So probably takes slightly longer than the previous one since there'll be slightly more overhead from using Snow instead of multi-core. All right. And we get comparable efficiency like before. And it did take slightly longer. OK. So that does take a bit longer than before. Again, that's primarily because we're reading data from disk. But is there anything we can still do to improve the speed of reading that data from disk? Well, one thing to note is what we're passing to each of these workers is the indices that make up the subsets that we're using to fit the data. And these indices are random. So for example, these are in a increasing but fairly random order. And that means that reading the data from disk will take longer than if these weren't random. And that's because when R goes to read the data from disk, it'll first have to read the 10th row of a data frame, then the 27th row, then the 47th row, then the 55th row. So that's a lot of jumping around. So that's going to be a lot slower than if we could say just read the first 100 rows. So reading data from disk is dramatically faster if we can do it sequentially rather than randomly. So one way that we could improve the speed here is if we permuted the data beforehand and then wrote the data to disk. In our case, we randomly generated the data in the first place, so we can kind of assume that the order doesn't matter. In practice, your data frame probably already has some sort of structure to it, so you would probably want to randomize it first and then write it to disk. In our case, it's already pretty random. So here, I'm just going to create some sequential indices rather than random indices. And then this is the same fit as before using Snow. The only difference is now the subsets are sequential, so they're chunks of the data frame rather than random subsets of the data frame. And that was approximately, I want to say, 4 or 5 times faster than it took before using with random reads. So that's one important thing to keep in mind if you use any sort of package that reads data from disk like this. All right, now to wrap up, I just want to quickly mention a few other packages for solving similar problems. So there's a package on Bioconductor called Delayed Array that Vince Carey talked about. It provides a flexible interface to other data on disk backends. The cool thing about Delayed Array is you can use it to essentially wrap any kind of matrix object, and then any operations that you do to it, say like adding a constant, multiplying by a constant, doing some sort of scaling, or getting a subset of it, all of those operations will be delayed and not actually evaluated until you actually try to access the data structure. And so that can be pretty efficient, because trying to do those every single time, especially if the data is stored on disk, that can take a while and cause a lot of slowdown. So that's the main cool thing about Delayed Array. You can use it to wrap just an ordinary R matrix. You could use it to wrap a matter object or some sort of other on-disk backend. So one other package to mention is HDF5 array. It basically provides a delayed array. It extends delayed array by providing an HDF5 backend. So if you have any data in like an HDF5 file somewhere, then HDF5 array is a great way to access it without having to load it into memory every time. Any questions on this quick scalability section here? All right, well, that wraps it up for the afternoon until our keynote. Thank you.